We just looked at bootstrap aggregation, or bagging, for regression, and now we'll take a look at bagging for classification. So it turns out that bagging can also very naturally be used for classification, and there are two essential approaches that you could take to use bagging for classification. So the first one is just a very straightforward approach. We take the majority vote. Remember when we were doing the regression case here, we had this sequence of data sets, and in our analysis we were assuming that they were drawn from the true distribution P, but then we approximated them by drawing bootstrap samples from the empirical distribution that we were estimating P by. And for each of those bootstrap samples, we constructed a, well, we were looking at a single point x, but we could have considered the whole range of x's and constructed a function to approximate this red function that we were trying to estimate. And instead, in classification, the y's will be in some finite set, and we will, for each data set, construct a classifier. So we'll get some sequence of classifiers. So maybe we call them C1 up to C, and we get some sequence of classifiers, and we would just, given a new point, so if we were given some new x, we would look at the class that each of the classifiers predicted for x and just take the majority vote. So just a very simple approach. Another possibility, which you can often use, is to average the probabilities, average the estimated probabilities. So for this approach, we need to have estimated probabilities to average. So instead of just getting a classifier, we're going to assume, for this approach, that we get for each classifier also defines some PMF on the classes. So let's denote them P1 up through PM. So each of these is a PMF on the set of classes. Maybe we call it this script y, just some finite set of classes. So we get these estimated PMFs, and we define, maybe we call it P hat or something, of a class y to just be the average of these estimated probabilities, just like we talked about. And this looks a lot like in the regression case. Remember, in the regression case, we had these yi's, each of which we had a yi for each data set, and we averaged them to get our z. And so if you think about each of those probabilities as one of these y's, then z is like the average estimated probability. So this, in fact, this is just in this case, averaging probabilities is just exactly like the regression case, except instead of a point x here, what we have the different classes y, and instead of y on this axis, we have the probability of the class. So that's some real number, the probability is some real number, and that's a regression problem in which we are estimating the true probability of y. True probability that a given, so we're assuming, as usual here, we have some x, some underlying x that we are evaluating these probabilities for. I should have mentioned that. We have some x that we're trying to predict the class, the associated class for. And to all of these, technically speaking, these all depend on x. So we're trying to predict the class of x, and we get a probability. There's some true probability mass function for x, and we estimate it. So this is just special. This is just turns out to just be the regression case. And so this analysis that we did before holds up, assuming that. So we had these key assumptions here that it was an unbiased estimator, and that it was a true function. And this might not hold in general for our estimated probabilities. In order for our analysis to work, then the estimated probabilities would have to be unbiased. But if we assume that, then it all goes through, and so the bagging technique, these estimated, so the aggregated probability is going to be a good estimator of the true probability. And then if we do the usual thing, to classify, we would just classify x as the most likely class according to this estimated probability. So that's how you can use bagging for classification. And I'd like to now describe if we were to drop. So we had these assumptions, and we also had this assumption. These were the main assumptions we made. So if we drop these two assumptions, but still keep this one, let's see what we can do with this analysis that we did to say something about how bootstrap aggregation helps us. So to drop this, so let's introduce, before we had x and y, right? We had x and there was some, so we had x and there was some true y. But now, and it was fixed, right? Because we assumed that there was this function, f of x equals y, some deterministic function. But now, let's say that instead of there being a deterministic function, that there is just a random variable. So we get there's an x and there's a w, something like that. Some random, maybe y would be better, but I'm already using y. So we get this w, which is the true thing, and we want to minimize. So we are going to construct then a y from our data set. We're going to construct a y for this x. Maybe we'll keep x. We won't make x random. Let's keep x fixed. And we get this random w, which is the true value, and we're trying to minimize this square loss. So we'll think about the regression case again. Well, that should be square outside. So we want to minimize this square, the expected square loss, so the risk here. And y is just the same generic y from the regression case from before. This was just, we get a data set and we have some procedure for producing a y for the given x that we're interested in. So y is our estimator of the class associated with x, except the problem now is that the class has some randomness. So it does not, this does not hold now anymore. And now let's see what we can say. So this we can write as, so we can add and subtract the expected value of y. And if we group the first part and the second part, and we multiply this out, what do we get? We get expected value of y minus its expected value squared, we get the square of this part, and then we get 2 times, so we get the expected value of 2 times their product. Oh, not a square there. And now this part, I didn't really say, but let's assume that this W, the true value that we're trying to estimate, that we're trying to predict, is independent from Y. So this expectation of the product becomes the product of the expectations, and so this part, the expected value of this, is 0. So this whole term becomes 0. And this is the variance of Y, and that's always greater or equal to 0 because the expected value of something non-negative is always non-negative. So what we get is that this whole thing is greater or equal to this expected value. So let's rewrite that. So we get the original thing, this is the true value that we're trying to predict, but it's random, greater or equal to this expected value, the mean of Y, minus W. So by replacing Y with its mean, we get this inequality. And now, think about this. What does this mean? What does this mean? This is, well, the mean of Y can be approximated by 1 over m of some IID draws from the same distribution as Y, right? Law of large numbers tells us that. And that is precisely Z. So Z, where Z is our aggregated estimator. So the aggregated estimator, we took these IID draws and we averaged them. So Z, right? So what Z am I talking about? Remember, this was in regression. We were talking about, we defined this aggregated estimator as the average of our well, in this case they're not bootstrap samples, they're actually IID Ys, one associated with each data set. That was our aggregated estimator. So Z approximates the expected value of Y. So this quantity is approximated by Z minus W squared. So this is saying that if we replace Y by its average, then we do better. We do better we have a lower expected loss for predicting the true value W, the random true value. And if this approximation is good, then by replacing Y by Z, by the aggregated estimator, then we will be able to reduce our expected loss. And so this is not assuming, remember, this is not assuming that we had a deterministic function. So instead the true value is random, depending, even for a fixed x, the true value is random. And this is also not assuming that the estimator is unbiased. So we're not assuming that the expected value of Y is W. Well, that wouldn't even really make sense since W is random. So this is another way to think about justifying bootstrap aggregation. And of course you would replace, the Z, you'd use bootstrap samples and use this justification.